take your seats, please. Fasten your seat belts. In case of an emergency, oxygen masks will. Okay. So this algorithm is well described in the book by Edelsbrunner and Harrer. I think the title is Computational Topology. They describe the algorithm. They also describe some ways to speed up the computation in certain cases to do it really efficient. And they say that you obtain the barcode if you do apply that what they call the elder rule. The elder rule is that when two components are merging, then we keep the component that has been born, that has been created earlier. We keep the elder component, and we cut off the younger one. So this is the elder rule, and applying this elder rule gives you a recipe to compute these numbers which constitute the barcode. I did not see in the book an actual justification why does that compute the barcode. I mean, it's only apply this rule, then you get the barcode. I did not see no proof and no justification other than do this, you get that. So I'm trying to convince you now using representation theory that we have to apply this rule. That's a plan, that's okay? Okay, very good. So basically the goal is understand the elder rule. So I want to understand that rule. So situation, say we compute H0 and we focus on the situation where we merge two connected components, call them C1 and C2. So these are two connected components in my graph. And say at some point in time, I merge them, I introduce one edge in my graph. So these two components get merged together into one component and they continue living together from there on. And I want to analyze this situation. Yeah, I mean, in general, I simplify a little bit. In general, you could, you have to analyze what happens if three components merge, but that is kind of the simplest case. Let's focus on this one. And the general case you can deduce similarly. That's okay? So, good. And we want to understand this in terms of representation theory. So H0 is a module, is a representation of the quiver, of the underlying quiver that has arrows here from left to right. And what is the module? So H0 counts the connected components. The dimension of H0 is the number of the connected components. So at this time step, sorry, I didn't want to erase it. At this time step, I have one connected component. So H0 here would be one-dimensional. Then a second component is born. At this time step, I have two connected components. H0 will be two-dimensional, yeah? And H0 also takes into account the map of the inclusion. So the first component stays here. This is one basis element of this two-dimensional vector space. So if I represent that by a matrix, this will be this matrix that maps the first K into the first component of this two-dimensional space, right? Are we good so far? So this is really how I read off the module in terms of matrices and linear maps from this merging picture here, okay? Then let's say they go live on parallel for some time. So if they live on parallel for some time, I go on with k squared, and I have identity between them. And then what happens if we merge the two components? So from k square, I go down to k, and the two components are merged into one. So the first basis element is mapped onto the basis here, and the second basis element is also mapped to the base here. So the matrix that I get for that merging is this matrix, which has got two ones. That makes sense? Okay, good. And then from there, I continue with identity 1, 1, 1, 1 forever. So this one is my module. That's what I'm given. Yeah. In general, the module might be higher dimensional, but the situation, the arguments will be similar. Let's focus on this case, okay? Good. So I'm given that module in terms of linear maps and bases. All is good. I only give myself an interpretation of the basis elements. Every dot here is a basis element, and this is how the maps act. Okay. So what I want to do now, I want to compute the barcode, and we saw that computing the barcode corresponds to decomposing the module into indecomposable summands. Yeah. So I want to compute the direct sum decomposition of this module, of this module H0, okay? So what is an obstacle to the direct sum? These are the two ones here, yeah? A direct sum is made of ones and zeros off diagonal. A direct sum is not made of two ones in the same row. At this moment, it's not a direct sum. I need to perform some base change in order to get a direct sum, in order to produce some zeros here. That's what we need to do. You agree to this? Okay, very good. So that's the goal. This is what we have to do. We apply, let me formalize this. So really what we want to do now, we are coming from this situation here, okay? And that gives me this module. And I want to do a base change in order to get rid of one of these two ones, yeah? And a priori, I don't know which one. So a priori, I could try to reduce from 1, 1 to 1, 0, or I could go from 1, 1 to 0, 1. Let's explore these two possibilities, right? Okay, so now I need you to help me. If I want to do the base change, say we first talk about the upper picture. I want to go from 1, 1 to 1, 0. So I need to come up with an invertible matrix such that the composition of this invertible matrix here, the composition of this invertible matrix, a 2 by 2 matrix, this matrix here, composed with the lower one, 1, 0, should be by commutativity, that should be the same as this way around. So that should lead to 1, 1. That's good? So I'm looking for an invertible matrix such that multiplied with 1, 0 on the left gives me 1, 1. Okay? Invertible matrices, upper triangular are the best ones. Then I don't need to think further about the determinant. Yes, I like to have an upper triangular matrix. And 1, 0 from the left, this means row operation. This means the first row should be this one, right? So I give myself a matrix whose first row is that, and which is a triangular matrix. Good candidate. You agree? Okay, very good. So I apply my base change here. That's what I can do. And let's try the same game down here. Okay, if I try the same game down here, I do a base change. I need to find a base change matrix that transforms the 1, 1 into a 0, 1. So what would be the equation down here? The equation down here would be, I'm looking for some matrix such that when I multiply it with 0, 1, I do get 1, 1, so same equation. And can you give me a solution for this one? Huh? The lower, so the second row this time must be 1, 1, yeah? And I want it to be a triangular matrix, so I do this matrix. That's good? Okay, so perfectly fine. The point is that locally, just here at this position, locally, I can do the base change like this or like that. Yeah. So locally at that moment, there's no preference if I kind of kill the second entry one or I kill the first entry one. I can do both in terms of linear algebra, just restricted to that point in time. Both are possible. No issue with that. That's okay. Okay, that's good. Then let's move to the left. Okay, if I move because you remember the notion of a representation. I mean, I have of a morphism of representations. I have a whole family of morphisms. Yeah, and for each of them, all the diagrams here, all the squares must commute. This is the condition. So the condition is not locally one square commutes. They need to commute all the way. That's good. Okay, so let's do that. So I go to the left here. Now having having the identity here, and the condition means it commutes, means I have to copy that same matrix here. Yeah. So whatever base change I do here, I need to do here all the way as long as there are identities. Yeah. Okay, good. So I've got the same matrix. I've got the same matrix 1, 1, 0, 1 here. Here I've got an invertible matrix from K to K. My field is Z2. I have not much choice. I've got an invertible matrix here. My field is Z2. I don't have much of a choice. And here I do my matrix 1, 0, 1, 1. So here I also do the matrix 1, 0, 1, 1. And then we only need to verify, do I have a morphism? Does this diagram commute? Does that diagram commute? Yeah? That's good? Let's do that. The first thing, this diagram commutes, so I go this way around. This gives me 1, 0. And I go the other way around. You can help me, I make mistakes with this linear algebra. That would be 1, 0 followed by my base change matrix 1, 1, 0, 1. That's good. I make no mistake. Okay, so is this one correct? Yeah, good. So that one works. Okay, let's check the other one. Let's check the second possibility. If I check the second possibility, I need to go this way around. This way around is 1, 0, and I ask myself the question, do I get the same thing from my base change matrix is 0, 1, 0, 1, 1, and we have 1, 0 coming from here, so I follow that composition. What do you say? No, it's not. It's not true. So this is not equal. So that does not work. That does not work. Yeah. So of these two possibilities of a base change that are at my disposal locally, only one of the two can be realized as a morphism of representation. I look for an isomorphism of representations into a direct sum. I need to respect these rules. Only the first one gives me the direct sum composition. The second one does not work. Okay? So what we learn from representation theory is that I can, in fact, delete here the second entry one. So I can delete the edge here that comes from the component that has been born at a later time. I need to keep the component that has been born before. Yeah. So I have to kill the younger one. I'm sorry for this. So this is not a rule made up by some old guys. It's really representation theory is dictating this rule. This is the direct sum decomposition. My apologies. Yeah. And if you were to try to do the base change that we do here, I mean, we delete this edge. Sorry, do you see that we delete this edge here? Then the base change would actually introduce another one here that would introduce a new edge here. So we clean up situation here, but then we create another edge here. This is just not a direct sum. So if you want to get a direct sum, this is what you have to do. That's the bottom line. Okay, that's good. So I think this is the explanation of the elder rule. Everybody agrees? Okay, perfect. A good rule. Yeah, good. So this was this. Thank you very much. And that kind of finishes really this part. We were discussing about the barcode and the elder rule, so we understand really why we need to apply this rule. And the one parameter case is now done. Thank you very much, finished. And I would like to talk a little bit about multiparameter case and the use of additive invariants, okay? Good, so maybe other questions so far up to here? No? So let's go on to multiparameter persistence homology. So there are some problems. There are some limitations of one parameter persistence. I mean, one parameter persistence is very good. It's very powerful. But Frederick was always a bit careful. I mean, it can be very helpful. It can give us some valid additional informations, but it always depends on the situation. It depends on the data. It's not guaranteed. It's no tool that works always. Yeah. And indeed, there are some limitations that you can see here. I mean, there's two examples of point clouds, X and Y. And what's the difference between X and Y? I mean, X looks like it is sampled from a circle or from an annulus, right? And if you compute the barcode and you compute H1 here, the barcode of the module H1, then you would expect a nice big circle to show up. And indeed, in the barcode, you find a nice long bar, which indicates, aha, I have a circle. Good. Now, difference between X and Y is you sprinkle some noise in the middle. Yeah. Like in real life data, I mean, there's always going to be some noise. And so that's really the difference between X and Y. They are not that much different. But if you look at their barcodes, this noise here is going to change totally my barcode description. So I had here this nice long bar, but now the noise will create some circles here and there and there, and I don't know where. So in the H1 of the noisy picture, you see a whole bunch of bars for H1 popping up, and the long bar has is gone. So there's a drastic change between these two pictures. Yeah, so it can be unstable under outliers. Okay. And also, if we compare these two, I mean, here we have like a circle plus some noise, and here I have just noise. Yeah. So I want them to be totally different, but I mean the barcodes. Sorry, the barcodes do not look that different. Yeah. I mean, yeah, I can say, okay, here's one little longer, but this is totally random. I mean, just from the barcode picture, I don't really have a good way to distinguish between these two. Yeah. So you can certainly produce pictures and examples where you see that just computing one parameter persistence doesn't do the job. Yeah. But anyway, you always want to use persistence theory as one additional piece of information. I mean, that doesn't solve all your problems, that's for sure. Okay. So these are the limitations, and there's many solutions to overcome those limitations. Like Frederick was talking about the distance to measure. This is a good way to do it. You can remove outliers via a density threshold. So if we could introduce some density parameter and just delete those middle noisy vertices which don't have a high density. So we remove outliers, then we go back to the original picture. Most of these approaches depend on some parameters. Often they depend on two parameters, and that dependence on several two or more parameters that motivates that we use bifiltrations. Yeah, filtration not only by one parameter but by two parameters. So we would really be looking at something like the filtrations that we had before, where we introduced those where we increased the radius, but also so here epsilon, the radius would go up here, and here we would introduce another parameter delta that would be depending on the density. So on the left-hand column, low density points like these two, they are ignored. They are not in the picture. So going from left to right, we introduce more and more points, or we going from right to left, we delete points that are not dense enough to get an overall picture. Yeah. So we can produce something like a two-parameter, a filtration that depends on two parameters. And this means really then we compute homology H0 or H1. And this really means then we compute a representation, a module over this poset, which is now the real number squared, yeah, R2. And our order relation is really going everybody who is to the northeast, who is up and right from a given point X, is considered larger than this point, okay? And as before, in one parameter persistence, we said for most of the time when we come from a finite data set, for most of the time, all the maps will be isomorphisms. So I shrink these isomorphic pieces, and there's only finitely many time steps where something happens, where the homology changes, and I fix only attention to these finitely many discrete time steps. So instead of R squared, I can look at the discrete grid, the poset, which is the product of an interval from 1 to n with an interval from 1 to n. So I have this grid here, an n times m grid, ordered like this to the right and upwards. Okay, so this is the situation we get when we look at bifiltrations associated to some set of data. Okay. The problem is, as we have seen, the barcode exists only for totally ordered sets. The barcode exists only when I have like one parameter. And in representation theoretic terms, these posets here, they are what they call wild. And in any case, there's no barcode available. There's no nice, simple visualization of the indecomposables. That's just not there. Yeah. So we have to find for other ways to describe, visualize the module that we get. Okay. One possible way to do that would be like go line by line. I mean, we can like we look at the module along this line and along that line and here, yeah. That would be kind of doing one parameter persistence theory with a fixed threshold, but we do this threshold at several steps, yeah. But this is kind of what we said we don't want to do, because a priori we don't know what is the good threshold, what is the meaningful for our data, and we wanted to keep this variable, yeah. Is there like a vector sequences, like where you compute one page and the next page and so on? No, not really. No, I mean this is really the honest. This is really the homology of a bifiltration. Yeah, you do your usual thing, computing homology, but now with two parameters. So you really get. I mean, what is a representation of this poset? A representation of that poset would be really a vector space at every point. You compute homology at every point each time, and you get linear maps now in both ways every time. It's a grid of maps. Yeah. So you could just fix along vertical or horizontal lines doing one parameter persistence theory. You get some information. That's okay. You could even say that you give yourself a line of a fixed slope. So I go from here to here, then I go from here to here. So I fix one line of fixed slope through that grid. And then I also have a module which depends only on one parameter. So I can do one parameter persistence theory on that line. Yeah. And there's a software available called Rivet, and this software is being developed by Mike Lesnick. And this is a beautiful package where you can you can really choose your line, you can choose your slope, and you can vary it. You can slide it through the module, you can change the slope. And every time you fix one line of a certain slope, like the blue one here, the software would compute the barcode to that along that one parameter. Yeah. So if we fix the blue line here, the software would compute H0, so a bar here and a couple of small bars here. They are visualized along the slope of the line. So if you change the line, if you would change the line somewhere here, the barcode would pop up somewhat in this way. Yeah. So you can slide your line through the two-dimensional plane, and every time some bars would pop up according to the one parameter persistence barcode on that one line. Okay. What the software also does is it gives you the dimension vector of the module. A module is given by vector spaces here, everywhere, at every point. Yeah. And the dimension vector is just what's the dimension of this vector space? Yeah. And it would give you in gray scales the dimensions. So lighter gray is smaller. So I imagine the light gray, I would have a one-dimensional space everywhere here. When it's higher, I would have a two-dimensional space, and here maybe a five-dimensional space. So darker colors indicate higher dimension of the module, and where there's nothing, the module will be 0-dimensional. So it gives a certain indication, how can we visualize, how can we see the module? At least the dimension is here, okay? And we will also get indication of the rank invariant. Okay, I'm gonna talk about this. And I get some indication of the Betty numbers. So there are certainly certain things that we need to explain. So let me talk about invariants. So what are the invariants that we would like to read off from such a module? Okay, so let's go there. Okay. Let's talk about invariants in all generality, and this is a bit of notation. So an invariant, an additive invariant on the category of representations of a poset P is a group homomorphism from what is called a group homomorphism phi from the split Grothendieck group of the representations of P into some abelian group. Yeah. I mean, these are vectors over some index set I are just vectors of some fixed size. And okay, so what is this split Grothendieck group? This is really the free abelian group, which has as a basis the indecomposable representations. And I want a group homomorphism, so I want a map phi that is compatible with the direct sum. I want that phi of direct sum m plus n is the sum of the phi values of m and n. So this is a group homomorphism. And so giving such a map on this free abelian group generated by the indecomposables would be meaning I give myself a map on every indecomposable, a value on every indecomposable, and then I just extend it linearly. Yeah, so really to every indecomposable, I want to attach a vector and then I sum them up. Yeah, so that's general invariance. And let's talk about examples. So the first example is the one which we already saw before, the dimension vector. Yeah, so the zeros example. When I have a module, I define an invariant phi of m to be the dimension vector of m, meaning this is the vector, the collection of the dimensions of the vector spaces at every point, just like that. Yeah. This is an invariant, it's a group homomorphism because the dimension of a direct sum will be the sum of the dimensions of each of the summands, so it's a group homomorphism. In representation theory, we call it the dimension vector. In TDA, it's often referred to as the Hilbert function of the module. And let's do some examples maybe. Let's do some examples. So I come back to one example. My poset P is a very simple grid, a 2x2 grid, okay? In this 2x2 grid, I give myself, over the 2x2 grid, I give myself a representation. So this is now referring to your remark. This means over every point here, I give myself a vector space. And along all the vertices, arrows, I give myself some linear maps. This is a module over that simple 2x2 grid. And by M, you have larger modules, but that's really what the representation is, okay? So let's consider the representation M here, given like this, with maps like that. And then what's the dimension vector? The dimension vector are the pointwise dimensions, yeah? So I've got dimension 1 here, 2 here, and 1, 1 here, and I just write them down in a nice diagram, yeah? I mean, do you allow me to call this a vector? I mean, you can arrange this in one row, but visually I find it nicer to arrange them in a square. That's okay? So this is one vector of 4 numbers, the 4 dimensions of these 4 vector spaces. That's all what it is, okay? What about the module N? The module N has dimension 1, 2, 1, 1. So the module N has the same dimension vectors as the module, as the representation M. the dimension vector cannot distinguish between these two representations. If I just look at these two representations from the perspective of the dimension vector, they are equal. They look equal. However, their maps are quite different. I mean, here I have a zero map. You see that? And I changed this one slightly. So if I compose here or there, which is commutative, the composition will be zero. And in persistent theory, I mean, this is the information we are interested in. We are not interested in the information what is present at this point. We are interested in how much of it persists when we move on through the diagram. Yeah. The dimension vector is totally insensitive to what persists. It doesn't see the maps at all. It sees only what's the dimension at this point. But maybe everybody who is born here dies immediately, and we don't see that. So the dimension vector in terms of persistent theory is really not a good invariant. Yeah. I mean, okay, it tells me I can visualize the module by the grayscale here. It's one-dimensional here and higher dimensional. That's very good. But it doesn't really tell me anything about persistence. So we want to find other invariants that are able to distinguish more modules, okay? And therefore, yeah, okay. So we want to be able to distinguish more modules so let me formulate this in a definition. So what do I mean? Distinguish more modules. Let's say I have got two invariants, so two such functions on the category of representations. I say phi is finer than the invariant psi if whenever psi is equal on two modules, then phi will be equal on those modules as well. Yeah, for all representations m and n. This is very mathematical definition. So whenever psi identifies, m and n cannot be distinguished using psi, then they can also not be distinguished using phi. But the other way around, it could be that phi is able to distinguish two modules that psi could not. Yeah. So phi is a finer information than psi. Phi will distinguish more modules than psi did. Okay. So that's what I'm looking for. And one example would be the rank invariant. And the rank invariant has been introduced by Carlson and Samarodian in 2008. And they say for my whole grid of my poset, I've got many points. Yeah, this is wrong here. Sorry, I did this yesterday evening. That's certainly not correct. So what I really wanted to say is I have this implication, but I do not have this implication. This is not an equivalence. So it could be that these two are equal, but they are different. Yeah? That's what you mean? Yeah. The lower one is fine, but it's the implication that should be the other way around. You want me to write this? Yeah, okay, I can do this. Everybody happy? This is my logic when I write up these things in the evening. Let's see what happens in the example, okay? Good. So let's introduce another invariant and then let's compare them. That's okay? Okay, good. So let me introduce the rank invariant. the rank invariant would be the invariant that I get when I measure the rank of the function that I get between any two comparable elements. So whenever I have two comparable elements, I and j in my poset, I got a linear map from mi to mj. This linear map has got some rank, and I just record this rank, this number, for every pair of comparable elements I and j. That's what I do. Okay. Remember that the map from I to itself was the identity map. Yeah. So the rank of the identity map is, of course, the dimension at this point. Yeah. So kind of computing the rank invariant includes the information of computing the dimension. Okay, let's do an example. Same poset, same modules. Let's compute the rank invariant. Okay, so to compute the rank invariant, no, I cannot change my color. To compute the rank invariant, I need to look at the rank of this map. This is 1. And I need to compute the rank of the map here on the left. This is a one-dimensional map. This is a rank 1 morphism. This is a rank 1 linear map. So my ranks will be 1 and 1 here. The map going up from here to here will be 1 as well. And what is the diagonal rank? If I go here, the diagonal map is 1 times 1. This is 1. The rank here will be 1 as well. You allow me to record the ranks in that kind of fashion. That's okay? Yeah. So these are all the ranks of all the maps, and it includes the ranks if I go from 1 to 1. So this is this one. This is just the dimension, and the rank from 2 to 2 is this one. This is just the dimension. Okay. So let's go back to this confusion what I was noting not right before. So I want to see that the rank is strictly finer than the dimension, because as we see, the information of the rank of all the ranks includes the dimension. Yeah. So if I compute all the ranks, in particular, I compute all the dimensions. If all the ranks are equal, then all the dimensions are equal. If all the ranks are equal, then certainly all the dimensions are equal. I have no space. If all the ranks are equal, then all the dimensions are equal. This is what I want to say. That's correct? Okay, so this is the correct implication. Is this what I had before? So that's good. Yeah, that's good. And but it, sorry. How do you fill the matrix of the ranks? I want in the matrix of the ranks. Yes, sure. In the matrix of the ranks, I want to record what is the rank of the linear map going from 1 to 2. This linear map, yeah? The rank of this linear map, I would like to write in that position. This is a rank 1 linear map. So this gives me the entry 1 here, okay? The map from 1 to 3 is this one here. It has got rank 1. So between 1 and 3, I would like to put it in that location in the matrix. That's okay? Yeah, so in my matrix, I would compute the rank from 1 to 3, from 1 to 2, from 2 to 4, from 3 to 4, diagonally from 1 to 4. So I organize my ranks in this fashion. Yeah? Okay, good. So we are okay with that inclusion, but okay. So what's the rank? What's the rank for n? What's the rank vector for n? What's the rank vector for n? I need volunteers. Who gives me the rank matrix for n for this one? Who volunteers? You have done already enough. Somebody else? Who volunteers to give me the ranks for the rank matrix for the module n? Huh? Come on. Don't let me down here. Come on. I don't need to come back to him. So what okay, come on, guys. What is the rank of this map here? It's 0. So you allow me to write a 0 here, down here. That's okay? Okay. What is the rank of the map going up here? 1. What's the rank of the map going up here? 1. What's the rank of the map going to the right on the top row? 1. What's the rank of the diagonal map? 0. 0 times 1 is 0. Okay, 0. And the dimension stays the same. That's what we know. So if I compare these two ranks, I see they have the same dimension, the blue things, yeah. But the rank information is different. They are not the same. Okay. So the rank invariant can distinguish these two modules, but the dimension could not distinguish them. Therefore, I call the rank is the finer invariant than the dimension. That's good? Is this now compatible with the version that I wrote here? Okay, good. Thank you very much. So we got that. Okay, perfect. Good. And so these are two examples of invariants that are realized in this software Rivet, the dimension vector and the rank invariant. And I would like to talk a little bit about how can we generalize these things using homological algebra. This is really my field where I am working. And we need to talk about some different interpretation of the dimension vector using projective modules and so on and so on. But I'm not going to do this today. So let me stop here. Thank you very much.